Looking up at the sky is humanity's oldest habit. And in that sky, as seen from Earth, the most striking object is the moon. The moon is not merely a satellite. It has shaped calendars, moved oceans, inspired poetry, mythology, and scientific revolutions. Since ancient times, humanity has looked at the moon and asked, how do we go there? For centuries, that question remained a dream. Until the mid-20th century. The late 1950s and early 1960s witnessed some of the fastest technological leaps in human history. Two superpowers, under the shadow of the Cold War, entered a race not only for arms but also for dominance in space. This competition became the driving force that enabled humanity to first set foot on a celestial body beyond Earth. In 1961, when Yuri Gagarin reached Earth orbit aboard Vostok 1, it was a wake-up call for the United States. President John F. Kennedy, in his historic address to Congress on May 25, 1961, declared, "I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth." The Apollo program was not a single mission but a series of carefully planned steps. Before any human could land on the moon, NASA needed to solve problems that had never been faced before. How do you launch a spacecraft toward the moon? How do you navigate over 380,000 kilometers of empty space? How do you land safely on an unknown surface? And most critically, how do you return? The Saturn V rocket became the backbone of Apollo. Standing 111 meters tall, it remains the most powerful rocket ever successfully flown. Its three stages worked in sequence, first to lift off from Earth, second to push toward orbit, and third to send astronauts on a trajectory to the moon. The command module carried the crew. The service module held life support and propulsion. And the lunar module was designed for one purpose only, to land on the moon and take off again. On July 20, 1969, Apollo 11 achieved what once seemed impossible. Neil Armstrong and Buzz Aldrin descended to the lunar surface while Michael Collins orbited above. Armstrong's first step was watched by over 500 million people on Earth. It was not just an American achievement. It was a human achievement. Apollo continued. 5 more missions successfully landed on the moon. 12 humans walked on its surface. They conducted experiments, collected rock samples, and drove the first off-world vehicle. But then, it stopped. After Apollo 17 in December 1972, no human has returned to the moon. The reasons were many. But the result was simple: humanity reached the moon, yet did not stay there. The year 1972 was coming to an end. Apollo 17 astronauts Eugene Cernan and Harrison Schmitt stood on the lunar surface for the last time. They had collected rocks, driven a rover, and looked back at Earth, a small blue sphere hanging in the blackness of space. Then they lifted off from the moon, docked with the command module, and began their journey home. Cernan, the last man to step off the lunar surface, said, "We leave as we came and, God willing, as we shall return, with peace and hope for all mankind." Those words would echo for decades. Because after that day, no one returned. The silence that followed Apollo was not accidental. It was the result of 3 converging forces: politics, economics, and shifting priorities. The United States had won the race to the moon. But once that goal was achieved, the national urgency dissolved. The Cold War was still ongoing, but the space race had reached its peak. There was no second prize to chase. President Richard Nixon's administration made a critical decision. NASA's budget, which had reached nearly 4.5% of the federal budget in 1965, began a steady decline. By 1975, it had fallen to less than 1%. The public, once captivated by moon landings, grew familiar. Television networks stopped covering Apollo missions live after Apollo 11. The question changed from, "Can we go?" to "Why should we go again?" NASA needed a new direction. Instead of launching massive Saturn V rockets for brief visits to the moon, the agency turned its attention to a new concept. A reusable spacecraft that could go to low Earth orbit regularly, carry satellites, conduct science experiments, and serve as a platform for assembly and repair. This became the Space Shuttle program. The Space Shuttle was not designed for the moon. Its engines, thermal protection system, and cargo bay were optimized for Earth orbit. The external tank and solid rocket boosters were discarded after each launch, while the orbiter itself returned to Earth like an airplane. It was an engineering marvel, but it was also a compromise. The shuttle could not go beyond low Earth orbit. The Moon, once a destination, was now out of reach. Meanwhile, the Soviet Union had also abandoned its own lunar ambitions. After several failed attempts with the N-1 rocket, which exploded 4 times without a successful flight, the Soviets shifted focus to space stations. Salyut and later Mir became their priority. Both superpowers had looked at the Moon and then looked away. Throughout the 1980s and 1990s, the Moon became a quiet subject. Scientists continued to study lunar rocks brought back by Apollo. They discovered new things, evidence of ancient volcanic activity, traces of water in glass beads, the Moon's internal structure. But no new missions followed. The Moon was no longer a destination. It was a past achievement, preserved in museums and archives. Humanity had reached another world, and then chose to stay home. For nearly 3 decades after Apollo, the Moon remained a distant memory. Human spaceflight had not stopped, but it had stayed close to Earth. Astronauts lived on the Mir space station. They built the International Space Station. They repaired the Hubble Space Telescope. All of this happened in low Earth orbit, just a few hundred kilometers above the surface. The Moon, more than 380,000 kilometers away, seemed almost irrelevant. But in the early 2000s, something began to shift. Quietly at first. Then with growing certainty. The idea of returning to the Moon began to resurface. In 2004, President George W. Bush announced a new vision for NASA. He called it the Vision for Space Exploration. The plan was ambitious: retire the Space Shuttle, complete the International Space Station, develop new spacecraft, and, most importantly, return humans to the Moon by 2020. This was not Apollo revisited. This time, the goal was not just to land and leave. The goal was to stay. To learn. To prepare for something even farther, Mars. But political priorities shifted. The vision for space exploration faced budget constraints, technical challenges, and changing administrations. In 2010, President Barack Obama canceled the Constellation program, which had been designed to implement that vision, and instead proposed a different path. The Moon, for a moment, was sidelined again. The new target became an asteroid. Then Mars. The Moon seemed to fade once more. Yet the idea did not die. International interest in the Moon was growing. China's Chang'e program began successfully orbiting and landing robotic missions. India, Japan, and Russia also announced lunar plans. Europe saw the Moon as a stepping stone. Scientists pointed to new evidence. The Moon had water ice in permanently shadowed craters at its poles. Water meant resources. Resources meant sustainability. The Moon was no longer just a symbol. It was becoming a destination again. On March 26, 2019, Vice President Mike Pence announced that the United States would accelerate its lunar plans. The new goal was bold: return humans to the Moon by 2024. The program had a new name, Artemis. In Greek mythology, Artemis was the twin sister of Apollo. The name was chosen carefully. Apollo had been about reaching the Moon for the first time. Artemis would be about building a lasting presence. Artemis was not a single mission. It was a framework. It included the Space Launch System, the heavy-lift rocket more powerful than any built since Saturn V. It included the Orion spacecraft, designed to carry astronauts beyond low Earth orbit. It included the Gateway, a small space station in lunar orbit. And it included human landing systems, built not only by NASA but by private companies. Artemis was structured to be sustainable, not repetitive. Each mission would build on the last. Each landing would teach something new. For the first time since 1972, a clear path to the Moon existed again. Not just a flag and footprints, but a plan. Artemis was announced not as a race, but as a collaboration. International partners were invited. Commercial companies were included. The goal was no longer simply to go. The goal was to stay. And this time, the moon would not be abandoned again. A rocket is not a single machine. It is a collection of systems, each designed to fail if the others do not perform perfectly. The difference between success and disaster is measured in milliseconds and millimeters. When NASA began building the Artemis program, there was no existing vehicle that could carry humans from Earth to the moon. The Saturn V was retired decades ago. The space shuttle could not leave low Earth orbit. Something new had to be built. Not just a rocket, but an entire system. In 2011, Congress directed NASA to develop a new heavy-lift rocket. The design was not entirely new. It borrowed technology from the Space Shuttle program, the main engines, the solid rocket boosters, the fuel tanks. But these components had to be reconfigured, strengthened, and adapted for deep space. The result was the Space Launch System, or SLS. Unlike the shuttle, which discarded its engines after each flight, the SLS would be expendable. Each mission would require a new rocket. At the same time, NASA was developing the Orion spacecraft. Orion had originally been part of the cancelled Constellation program. It was designed to carry 4 astronauts for up to 21 days without docking to a space station. It had a heat shield capable of withstanding re-entry speeds of 40,000 km per hour, faster than any human spacecraft since Apollo. Orion could go to the Moon, to an asteroid, or even to Mars. But first, it had to be tested. The Space Launch System has several configurations. The initial version, Block 1, can lift 95 metric tons to low Earth orbit. That is more than any rocket currently in operation. The upper stage, called the interim cryogenic propulsion stage, sends Orion toward the Moon after the core stage separates. Future versions, Block 1B and Block 2, will increase that capacity to 105 and 130 metric tons respectively. By comparison, the Saturn V could lift about 140 metric tons. SLS is not larger, but it is modern. Orion consists of 3 main parts. The crew module is where astronauts live and work. It is larger than Apollo's command module and has more advanced avionics. The European service module provides power, propulsion, thermal control, and life support. It is built by the European Space Agency, a rare example of international contribution to a NASA crew vehicle. The launch abort system sits on top. In an emergency during launch, it can pull the crew module away from the rocket in milliseconds. Testing was rigorous. In 2014, Orion flew for the first time on Exploration Flight Test 1. It launched on a Delta IV Heavy rocket, reached an altitude of 5,800 kilometers, farther than any human spacecraft had gone in 40 years, and splashed down in the Pacific Ocean. The heat shield worked. The parachutes deployed. Orion was ready. The SLS core stage underwent a series of green run tests in 2020 and 2021 at the Stennis Space Center. The engines fired for 8 minutes, the same duration they would burn during an actual launch. Engineers watched every sensor, every temperature reading, every vibration. There were delays. There were technical problems. But eventually, the system passed. Every piece of Artemis, the rocket, the spacecraft, the boosters, the service module, was designed for one purpose: to leave Earth and never look back. Not because the spacecraft would not return, but because its mission lay beyond. The Moon was waiting. But before anyone could go, the machine had to prove itself. Each part was a small beginning of a long journey. The International Space Station orbits about 400 kilometers above Earth. It has been continuously occupied since November 2000. It has hosted astronauts from 19 countries. It has supported thousands of scientific experiments. But the ISS was never designed to go farther. Its orbit is tilted, its speed is matched to Earth, and its shielding is meant for low Earth orbit's radiation environment. If humanity wanted to live and work around the Moon, a new kind of station was needed. Not a destination itself, but a way station. A gateway. The idea of a lunar orbiting station is not new. In the 1960s, NASA studied something called the Lunar Orbital Station. In the 1990s, there were proposals for a space station Freedom-derived lunar outpost. None of these concepts left the drawing board. But in 2017, NASA formally proposed the Lunar Orbital Platform, Gateway. By 2018, the name had shortened to simply Gateway. International partners quickly joined. The European Space Agency, the Canadian Space Agency, the Japanese Space Agency, and others agreed to contribute modules, robotics, and fuel. Gateway was not designed to be continuously occupied like the ISS. Instead, it would be periodically visited. Astronauts would travel to Gateway aboard Orion. Stay for weeks or months, conduct research, prepare for surface missions, and then return to Earth. Between crewed visits, Gateway would operate autonomously. This approach reduced cost and complexity while still providing a permanent human presence in lunar orbit. Gateway is modular. The first two components are the Power and Propulsion Element, PPE, and the Habitation and Logistics Outpost, HALO. PPE is a high-power solar electric propulsion spacecraft. It uses xenon ions, not chemical fuel, to move. This is far more efficient than traditional thrusters. HALO is a small living space, roughly the size of a one-bedroom apartment. It provides life support, docking ports, and command functions. Both are scheduled to launch together on a SpaceX Falcon Heavy rocket no earlier than late 2025. Later modules will expand. Gateway. The International Habitation Module, IHAB, is being built by ESA and JAXA. It will add more living and working space. The Canadian Space Agency is providing Canadarm3, a robotic arm system for maintenance and external operations. The European system providing refueling. Infrastructure and Telecommunications, ISPRI, will add refueling and high-speed data links. A crew and science airlock will allow astronauts to perform spacewalks without venting the entire station's atmosphere. Gateway's orbit is unique. It will not be a simple circle around the Moon. Instead, it will use a near-rectilinear halo orbit, NRHO. This orbit brings Gateway as close as 3,000 kilometers to the lunar surface at one point and as far as 70,000 kilometers at another. The advantage of NRHO is stability. Gateway can remain in this orbit with very little fuel. It also provides constant communication with Earth and access to the lunar South Pole, the target region for Artemis landings. Gateway is not the Moon. It is a bridge to the Moon. From this small station, astronauts will descend to the surface. They will launch again to return. They will prepare for longer missions. They will learn to live in deep space. The idea of a permanent presence around the Moon, once a theory, then a drawing, then a proposal, was finally becoming real. Not as a flag. As a foothold. Before any human rides a new spacecraft, the machine must fly alone. It must endure launch, deep space radiation, high-speed re-entry, and ocean recovery, all without a single person on board. If something fails, no lives are lost. But if everything works, the path opens for the crew. This is the logic that shaped Artemis I and Artemis II. One mission without humans. One mission with humans. Both designed to test the system before the landing. Artemis I was originally scheduled for 2017. Technical delays, budget overruns, and the COVID-19 pandemic pushed the launch further and further. The SLS core stage faced years of testing. The Orion spacecraft required repeated checkouts. By 2022, the rocket had spent more than a decade in development. Critics called it too slow. Supporters called it careful. Both were correct. On November 16, 2022, at 1:47 a.m. Eastern Time, Artemis I finally launched from Kennedy Space Center's Launch Complex 39B, the same pad that had once launched Apollo 10 and Apollo 17. The SLS roared to life with 8.8 million pounds of thrust. The solid rocket boosters burned for 2 minutes. The core stage separated. The interim cryogenic propulsion stage fired twice to send Orion toward the Moon. The spacecraft was on its way. Artemis I was not a simple loop around the Moon. Orion traveled farther than any human-rated spacecraft had ever gone. It flew 450,000 kilometers from Earth, 40,000 kilometers beyond the far side of the Moon. The mission lasted 25 days, 10 hours, and 53 minutes. Orion entered a distant retrograde orbit. which took it 70,000 kilometers past the lunar surface. This orbit is stable and requires little fuel, exactly the kind of trajectory that Gateway will use. During the flight, engineers tested every critical system. The solar arrays deployed and generated power. The propulsion system fired precisely for trajectory corrections. The thermal control system kept the spacecraft at the right temperature despite extreme swings between sunlight and shadow. The star trackers and navigation cameras confirmed Orion's position in deep space. The communication system sent high-definition video from 430,000 kilometers away. The most critical test came at the end. Orion re-entered Earth's atmosphere at 40,000 kilometers per hour, the speed of a lunar return. The heat shield experienced temperatures of nearly 2,800 degrees Celsius, about half the surface temperature of the Sun. The avionics guided the spacecraft through a skip re-entry. Orion dipped into the atmosphere, lifted out, and then descended again. This maneuver reduced G-forces on the crew and landed the spacecraft closer to the recovery zone. 12 parachutes deployed in sequence. On December 11, 2022, Orion splashed down in the Pacific Ocean off the coast of Baja California. Recovery teams retrieved the spacecraft within hours. Artemis II will repeat much of this flight, but with 4 astronauts on board. The crew was announced in April 2023, Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and mission specialist Jeremy Hansen of the Canadian Space Agency. Glover will be the first person of color to leave low Earth orbit. Koch will be the first woman to do so. Hansen will be the first Canadian. Artemis II will not land. It will fly a similar trajectory to Artemis I, testing Orion's life support, manual controls, and crew interfaces. The launch is currently scheduled for no earlier than September 2025. Artemis I proved the machine could fly. Artemis II will prove that humans can survive the journey. Neither mission will touch the moon. But without them, no landing is possible. Each test laid the foundation for the next step. Each success made the return to the lunar surface one step closer. The path was being tested. And so far, it held. No human has walked on the moon since December 1972. That is more than 50 years. An entire generation has been born, grown up, and grown old without ever seeing a live image of a human standing on another world. The footprints left by Apollo 17 astronauts Eugene Cernan and Harrison Schmitt are still there, unchanged, sharp, preserved by the vacuum of space. No wind has blown them away. No rain has washed them out. They remain exactly as they were left. But they remain alone. Artemis III intends to change that. When the Artemis program was announced in 2019, the goal was a human landing by 2024. That deadline proved unrealistic. Technical challenges, legal disputes over the human landing system, and budget uncertainties pushed the date back. In 2021, NASA selected SpaceX to develop the Human Landing System, HLS, based on the Starship vehicle. Blue Origin and Dynetics had also submitted proposals, but SpaceX won the contract. Blue Origin filed a lawsuit, which delayed work for several months. The lawsuit was ultimately dismissed, and development resumed. By 2024, NASA had revised the landing date to no earlier than September 2026. Some independent reviews suggest 2027 or later is more likely. But the mission architecture is now largely fixed. Artemis III will be the first test of the full system, SLS, Orion, Gateway, and HLS working together as an integrated transportation network. The mission profile for Artemis III is complex. First, the SLS launches Orion with 4 astronauts from Earth, while the crew travels toward the Moon. Several other components are already in place. The HLS Starship, modified for lunar landing, waits in lunar orbit. It does not launch from Earth. Instead, it is refueled in orbit by multiple tanker flights. This is necessary because Starship is heavy. To reach the Moon with enough propellant to land and take off, it must be refueled in space. Orion docks with the Gateway. 2 astronauts transfer to Starship HLS. The other 2 remain on Gateway or in Orion. The HLS descends to the lunar surface, targeting the South Pole region, specifically an area near Shackleton crater or the connecting ridges. This region is scientifically valuable because it contains permanently shadowed craters with water ice. It is also challenging. The sun stays low on the horizon, creating long shadows and difficult lighting conditions. The two astronauts will spend approximately 6.5 days on the lunar surface. This is far longer than any Apollo mission. Apollo 17 had the longest surface stay at just over 3 days. Artemis 3 will allow twice that time for exploration, sample collection, and scientific experiments. They will wear new generation spacesuits, the Exploration Extravehicular Mobility Unit, or XEMU, designed for greater mobility, better dust protection, and longer life support. After completing surface operations, the HLS ascent stage lifts off from the Moon. It docks with Orion. The two astronauts transfer back. The HLS is discarded. Orion fires its engines to return to Earth. The landing site? The Pacific Ocean, just as with Apollo and Artemis I. Artemis 3 carries a symbolic weight that extends beyond science. NASA has stated that the crew will include the first woman to walk on the Moon and the first person of color. The names have not yet been announced. But the message is clear: the lunar surface, once touched only by white American men, will welcome a more diverse human presence. The Moon does not care about the color of a spacesuit or the accent of the voice inside it. But the people on Earth do. And Artemis 3 will show that the Moon belongs to all of humanity. The surface was waiting. Soon, it will receive new footprints. Why return to the Moon? This is the question that every space agency, every politician, and every taxpayer asks. Apollo answered one question: can we go? Artemis must answer a different question: should we stay? The answer is not sentimental. It is practical. The Moon is not just a destination. It is a resource, a laboratory, a proving ground, and possibly a stepping stone to Mars. To understand why the Moon matters, one must look not at the past, but at the future. For decades, scientists suspected that the Moon was completely dry. The Apollo samples returned between 1969 and 1972 contained no detectable water. This fit the theory: the Moon formed from a giant impact, and any water would have been vaporized. But in the 1990s, new missions began to challenge this assumption. In 1994, the Clementine mission used radar to detect signs of water ice in permanently shadowed craters at the lunar South Pole. In 1998, Lunar Prospector found hydrogen signatures consistent with water ice. The evidence grew stronger. In 2009, NASA deliberately crashed the ICROSS spacecraft into a shadowed crater near the South Pole. The impact plume contained water vapor. Later, India's Chandrayaan-1 mission confirmed the presence of water molecules on the surface. The Moon was not dry. It held water, locked in ice, hidden in shadows, scattered in tiny grains. This discovery changed everything. Water is heavy to launch from Earth. But if water already exists on the Moon, it can be used for drinking, for growing food, and most importantly, for rocket fuel. The lunar South Pole is unlike the equatorial regions where Apollo landed. At the equator, the sun beats down for 2 weeks, followed by 2 weeks of darkness. Temperatures swing from 120 degrees Celsius to minus 170 degrees Celsius. At the South Pole, the sun never rises high. Some crater rims receive nearly continuous sunlight. These peaks of eternal light are ideal for solar power. But just a few kilometers away, inside deep craters, sunlight never reaches. These permanently shadowed regions are among the coldest places in the solar system at minus 230 degrees Celsius. Water ice has accumulated there over billions of years, delivered by comets and asteroids. If that ice can be extracted, it can be split into hydrogen and oxygen through electrolysis. Hydrogen and oxygen are the same propellants used by many rocket engines. A lunar refueling station could dramatically reduce the cost of deep space missions. A spacecraft leaving Earth must push its fuel against Earth's gravity. A spacecraft leaving the Moon only faces 1/6 of that gravity. Launching from the Moon requires far less energy. The Moon becomes a gas station, not for cars, but for missions to Mars and beyond. Science also drives lunar exploration. The Moon preserves a record of the early solar system that Earth has erased. Plate tectonics, volcanism, and weather have destroyed most of Earth's ancient rocks. The Moon has no atmosphere, no water, no life. Its surface is a time capsule. By studying lunar craters, scientists understand the bombardment history of the inner solar system. By analyzing lunar samples, they learn about the formation of Earth-Moon system. By placing seismometers on the Moon, they study its internal structure, and by extension, the early evolution of rocky planets. The Moon is also a testbed for Mars. Mars is 3 years round trip with current technology. The Moon is 3 days. Any technology needed for Mars, life support. Radiation protection, habitat construction, resource extraction, can be tested on the Moon first. If something fails on the Moon, astronauts can return to Earth in days. If something fails on Mars, rescue is impossible. The Moon is not a distraction from Mars. It is a prerequisite. The Moon is not a destination. It is a beginning. Water, energy, science, and preparation, these are the reasons to stay. Artemis is not about repeating history. It is about creating a future where humanity does not live on one planet alone. Artemis will land humans on the Moon. But then what? The program was never designed to end with a few footprints and a flag. The architecture, SLS, Orion, Gateway, HLS, was built for sustainability. Each mission is meant to follow the last. Each landing is meant to enable the next. Artemis is not a sequel to Apollo. It is the first chapter of a longer story. A story that leads not just to the Moon, but to Mars. And perhaps, one day, beyond. NASA has published a roadmap for lunar exploration that extends through the 2030s. Artemis 3 lands at the South Pole. Artemis 4 will deliver the IHAB module to Gateway and conduct another surface mission. Artemis V will add Esprit and the Canadian robotic arm, followed by more landings. Each mission increases capability. Each mission tests new technology. By the late 2020s, NASA intends to have a permanent, sustainable presence on the Moon, not a base in the sense of a single building, but a distributed network of habitats, rovers, power systems, and resource extraction facilities. International partners are already planning their contributions. The European Space Agency is developing a lunar communications and navigation system called Moonlight. Japan is designing a pressurized rover that can carry astronauts across the lunar surface for weeks at a time. The United Arab Emirates is building an airlock for Gateway. China, operating independently with its own International Lunar Research Station, plans to land its first astronauts by 2030. The Moon is becoming a destination for many nations, not just one. The long-term vision for the Moon includes 3 critical capabilities: power, mobility, and resource utilization. Power means nuclear. Solar panels work at the poles, but not in permanently shadowed regions. NASA is developing the Fission Surface Power Project. A small nuclear reactor that can generate 40 kilowatts of electricity, enough to power several habitats continuously for years. Mobility means pressurized rovers. Unlike the open rovers of Apollo, which required spacesuits, pressurized rovers allow astronauts to live inside for days or weeks, traveling hundreds of kilometers from the landing site. Resource utilization means extracting water from ice, processing it into hydrogen and oxygen, and storing it as propellant. This is the single most important capability for sustainability. Once water mining is operational, the Moon becomes self-supporting. From the Moon, Mars is the obvious next target. The distance is vastly greater, 225 million kilometers on average compared to 384,000 kilometers. The journey takes 7 to 9 months one way. Communication delay is 5 to 20 minutes each way, making real-time control from Earth impossible. Mars has a thin atmosphere, not thick enough to breathe, but thick enough to create heat during re-entry. Landing on Mars is one of the most difficult engineering challenges ever attempted. Every Mars rover landing has been described as 7 minutes of terror. But the Moon provides a rehearsal. On the Moon, astronauts learn to live off the land. They test habitats, spacesuits, and life support systems. They practice surface operations in low gravity. They prove that humans can survive beyond Earth for extended periods. When NASA's Mars mission finally launches, currently envisioned for the late 2030s or early 2040s, it will carry the lessons learned on the Moon. The two destinations are connected. The Moon is not a detour. It is the path. Beyond Artemis lies a future that is not yet written. Permanent lunar bases. Regular flights to the Moon. Commercial mining operations. Scientific outposts. And eventually, the first humans on Mars. Artemis is the beginning of that future. Not because it is perfect, but because it exists. The rockets are built. The spacecraft are tested. The partnerships are formed. The path is clear. This journey was never just about the Moon. It was about what lies beyond, the unknown. And the unknown, as always, is waiting.
Write your questions in the comments. Subscribe to our channel and turn on notifications for upcoming episodes of the documentary series. New documentaries are released every Wednesday and Friday on this channel.